Hello, let's start chapter 1, real numbers. In this chapter, we will learn about real numbers. We'll learn about the fundamental theorem of arithmetic and the main applications of fundamental theorem of arithmetic. First, we can use it to prove the irrationality of many of the numbers that you guys have studied in class 9th. And secondly, we can apply this theorem to explore when exactly the decimal expansion of a rational number is terminating and when it is non-terminating repeating. So let's start the chapter with the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic. In your earlier classes, you have seen that any natural number can be written as a product of its prime factors. So for example, 2 can be written as 2 only. There are no other prime factors of 2 other than 2 and 1. And 4 can be written as 2 into 2. Then 253 can be written as 11 into 23 and so on. Now let us try and look at the natural numbers from the other direction. That is, can any natural number be obtained by by multiplying by prime numbers? Let's see that. So they have taken a collection of prime numbers, let's say 2, 3, 7, 11, and 23, and if we multiply sum of all of these numbers, allowing them to repeat as many times as we wish, we can produce a large collection of positive integers. So, for example, here we have taken three numbers out of these five prime numbers 7, 11, and 23. If we multiply 7, 11, and 23, we get this number. We get a positive integer. Similarly, if we multiply these four numbers, we get this, and so on. Now let us suppose your collection of prime numbers include all the possible primes. So what is your guess about the size of this collection? Well, in fact, there are infinitely many primes. So if we combine all these primes in all possible ways, we will get an infinite collection of numbers. Okay. Here they have shown how to factorize. So they have taken a big number here, 32760, and then they have done the prime factors of this. We have got these many prime numbers. Okay. So this number 32760 is a product of these prime numbers 2 cube 3 square multiplied by 5 multiplied by 7 multiplied by 13. Now let us try another number. Say this can be written as this. Of course we have to check that this and this are 3803 and 3607 are primes. You can try. So what does the fundamental theorem of arithmetic actually says? It says that every composite number can be expressed or factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. So any composite number can be expressed as a product of prime numbers, and this factorization is unique. So here they have, for example, this they have taken earlier. We took this example 32760, a composite number we have, and it can be written as a product of these prime numbers. So now they have given an example. Consider the number 4 raised to power n, where n is the natural number. Check whether there is any value of n which ends for which 4 raised to the power n ends with the digit 0. Okay. So if the number 4 raised to the power n for any n were to end with the digit 0, then it would have been divisible by 5, right? So now that is the prime factorization of 4 would contain the prime factor 5, should contain the prime factor 5. This is not possible because 4 raised to power n is nothing but 2 raised to power 2 n. So the only prime factorization of 4 raised to power n is 2. So the uniqueness of fundamental theorem of arithmetic guarantees that there are no other primes in the factorization of this. So there is no natural number for which 4 raised to power n ends with the digit 0. You can try it yourself. Now let's move further here. Okay, you have already learned how to find the highest common factor and the lowest common factor of two positive integers using the fundamental theorem of arithmetic. Now this method is also called the prime factorization method. Let us recall this method through an example. Okay, so here they have given an example where we need to find the lowest common factor and the highest common factor of 6 and 20 by the prime factorization method. So for 6 we can write 6 as 2 into 3, and 20 we can write as 2 into 2 into 5, which is nothing but 2 raised to power 2 into 5. So you can find the HCF of 6 and 20. Highest common factor of these two numbers is 2, right? And the lowest common factor of these two numbers is 2 into 3 into 2 into 5, right? Which is 60, as we have learned in the previous classes. So HCF is the product of the smallest power of each common prime factor in the number. So here the product of the smallest power of each common prime factor. Here the common prime factor is 2 and the lowest power or the smallest power of that common factor is 2. So highest common factor is 2 here. And LCM is the product of the greatest power of each prime factor involved in the numbers. Now here um, we have the common factor 2 here, right? But the highest power of this prime factor is here, which is 2 raised to power 2. So we have taken 2 raised to power 2, and other prime factors is 3 and 5. So 3 and 5. So this becomes our lowest common multiplier, LCM, and this becomes highest common factor. Okay. Now let's move on to the another example where we need to find the HCF of 96 and 404 by the prime factorization method. Okay, so 96 can be written as 2 raised to power 5 into 3, and the prime factors of 404 is 2 raised to power 2 into 101. So therefore the highest common factor we have here is 2 raised to power 2, because uh, the the common prime factor here is 2, and the lowest power of 2 is 2 square. So 4 is our highest common factor. Now let's find the LCM of these two numbers. LCM can also be found by this formula, which is multiplication of these two numbers divided by the highest common factor. So it becomes 9,696. Let's move on to the other example. This LCM you could have find by this earlier approach also, the product of the greatest power of each prime factor. So if we take the greatest power of each prime factor, then 101 multiplied by 3 multiplied by 2 raised to power 5 will give you 9,696. You can try that. Next is find the HCF and LCM of 672 and 120. So here the prime by using the prime factorization method. So let's find out the prime factors of these three numbers. So 6 can be written as a product of 2 into 3. 72 can be written as a product of 2 raised to power 3 into 3 square. And 120 can be written as this. Now here, to find the HCF, we need to take the smallest power of the common factor. So common factor here is 2 and the lowest power it has is 2. So 2, then other common factor is 3, so we can take 3. So 6 is the HCF here. Now we need to find the LCM. So for LCM, we will take 2 raised power 3 multiplied by 3 raised power 2 multiplied by 5. And this multiplication will give us the LCM, which is 360. Okay, they have also, so we need to notice that the multiplication of these three numbers is not equal to HCF into LCM. So the product of three numbers is not equal to the product of the HCF and LCM. Okay, now they have given some questions to try, which you can try on your own, and if you have any doubts solving this, and you can mention in the comment box and I can provide you the solution for that. Let's move on to the next topic, which is the irrational numbers. So, okay, in class 9th, you were introduced to the irrational numbers and many of their properties. You have studied about their existence and how the rational and irrational together made up the real numbers. So, you even studied how to locate irrationals on the number line. However, we did not prove that they were irrationals. In this section, we will prove that these numbers are irrational where p is a prime number. One of the theorem we use in our proof is the fundamental theorem of arithmetic. Recall a number s is called irrational if it cannot be written in the form of p upon q. So a number can be called irrational if it cannot be written in this form p upon q, where p and q are integers and q is not equal to 0. Some examples of irrational number which you are already familiar are under root 2, under root 3, under root 15, and so on. Before we prove that square root 2 is irrational, we need the following theorem whose proof is based on the fundamental theorem of arithmetic. So next theorem is, let p be a prime number if p divides a square, then p divides a, where a is a positive integer. Then here they are proving this theorem. Let the prime factorization of a be as follows. So here they have assumed, they are trying to assume here that let's say the prime factorization of a is p1, p2 multiplied by pn and so on, and these all are the prime numbers, not necessarily distinct. Therefore, a square will be multiplication of these, and I mean we will take these twice, p1 raised power 2, p2 raised power 2, and so on. Now we are given that therefore now we are given that p divides a square. Therefore, the fundamental theorem of arithmetic, it says it follows that p is one of the prime factors of a square. However, using the uniqueness part of the fundamental theorem of arithmetic, we realize that the only prime factors of a square are these. So p is one of the prime factor, one of these factors. Now, since a is equals to this, then p should divide a, right? We are now ready to give a proof that square root 2 is irrational. The proof is based on a technique called proof by contradiction. So here they are trying to prove that square root 2 is irrational, and let us assume to the contrary that this is rational, this is a rational number, So we can find integers r and s where s is not equals to 0 such that this number can be written as r divided by s. Now suppose r and s have a common factor other than 1. Then we divide by the common factor to get square root 2 equals to a upon b, where a and b are both co-prime numbers. So we can write this as b square root 2 is equals to a. Squaring on both the sides and rearranging, we will get 2b square equals to a square. Therefore, 2 divides a square. Now by the theorem, it follows that if 2 divides a, so we can write a is equals to 2c for some integer c, let's say. Now substituting for a, we get 2b square equals to 4c square. That is b square equals to 2c square. This means that 2 divides b square, and so 2 divides b, again using that theorem with b equals to 2. Therefore, a and b have at least 2 as a common factor, but this contradicts the fact that a and b have no common factors other than 1, because now we have find out that there is there is a number 2 which is a common factor here for a and b. But this is now contradiction. This is now a contradiction. So arisen because of our incorrect assumption that square root 2 is rational. So we can conclude that the square root 2 is irrational. Similarly, they have tried to prove that the square root 3 is irrational. You can go through it, and yeah, some more examples they have given. Similarly, you can prove using the contradictory theorem, and then they have given an exercise which has, I think, 2-3 questions to prove that these numbers are irrational. So in this chapter, what have we learned? We have learned about the fundamental theorem of arithmetic, and we have learned that if p is a prime number and q divides a square, then p divides a, where a is a positive integer. And then we have learned how to prove square root 2, square root 3, etc. are irrationals using the contradictory theorem, right? So, and that's all about the first chapter. If you have any queries solving any question, you can mention in the comment section and I will provide you the solution. Thank you